Hello everyone and welcome to my living room. I'm here as always with my trusty mug, and today we're going to talk about fiber. So let's go ahead and get started. Last time we talked about starch modifications and the idea that you could construct or deconstruct glucose polymers to get the size and functionality that you wanted. And today we're going to talk a little bit more about some glucose polymers. We talked last time about dextrose equivalents as well, the idea that if you have glucose units, just monosaccharides, that's 100 in terms of a DE, and then starches, which are very, very long glucose polymers, are practically 0. All right, so today's learning objectives are to talk about fiber, to look at derivatives of cellulose, and then also to introduce this idea of hydrocolloids. So according to FDA, fiber is generally a soluble or insoluble carbohydrate with 3 or more sugar units and lignin. So this is something new. So I want to just make sure that you're aware of what FDA considers to be a fiber. And here is one example of a fairly small molecule. And depending on how you modify it, this molecule could be Stachyose or Raffinose. These are two factors in beans that tend to make them musical fruit, so to speak. So if you have 2 galactose units, it's called Stachyose. If you have 1 galactose unit, that's Raffinose. But the fact that these are beta bonded to a sucrose molecule makes them very hard to digest, and thus some of their digestive properties. So again, this is this idea of the factor that's present in beans and produces gas. Inulin is another type of fiber. It can be very small, just 2 fructose units, beta bonded, or it can be fairly large, up to 60. The place that we typically source this would be banana peels, quite a bit of inulin in those. And it's considered to be what's called a prebiotic in the sense that it provides fuel for microbes that we actually want to have grow in our gut. So I'm not suggesting you go run out and eat a bunch of banana peels, but certainly this is where we get inulin from typically. If you eat too much of it, like most any of these fibers that we're going to discuss, you can get some GI discomfort and other symptoms that you probably know pretty well. All right, what does non-digestible mean? So FDA's definition includes the word non-digestible. I just want to make sure that you're aware that what it means is non-digestible by our human digestive tract. So from our teeth, mouth, esophagus, stomach, through our small and large intestine, it means that our human digestive capabilities cannot degrade these materials we call fiber. However, in our large intestine, there are many microbes that are waiting to do that job, and they have no problem taking apart these molecules for the most part. So just to let you know, non-digestible means non-digestible in human terms, but not in terms of the microbial flora that live inside of our large intestines. FDA has approved a number of fibers, and a number of others are pending approval. So some of these in the approved list should be very familiar to you. Beta-glucans, things like oats, for instance, psyllium, cellulose, guar gum, pectin, logos gum. If you're not super familiar with them, you've probably seen these on a label at one time or another. And then various forms of cellulose. Now, the ones that are pending are mixed fibers rather than single types of fiber, but mixed fibers from fruit or vegetable sources. And then you can see a number of others, some of which we will discuss. And actually, one we already did discuss, which was inulin. And of course, there at the bottom you can see polydextrose. So we have talked about a few of those, and so there you go. All right. So lignin. Lignin is something that bears discussing because it's not really a traditional carbohydrate. And so I want to show you what lignin looks like, because it makes up a major part of plant material, but it is quite different in terms of its composition and its chemical makeup. So here's lignin. It's primarily composed of 3 different types of alcohol, so paracoumaryl, coniferyl, and synepyl alcohol in a very complex structure. This is just one of many potential structures. It's not the lignin, but it's one of one type of lignin. And you can see if you look closely that over on the upper part of that it says carbohydrate. So maybe it's linked to a carbohydrate. But this is a pretty complex molecule, and it varies greatly in structure. But this is part of what FDA considers to be fiber. All right, benefits. So fiber does have benefits for human health, and they include the following. Benefits that are related to blood glucose and cholesterol control, to blood pressure. And so you can think about both diabetes and heart disease, two major concerns for chronic disease. And then, of course, laxative effects on mineral absorption, and then also effects on energy uptake. If you're full as a result of consuming a lot of fiber, perhaps you'll consume fewer calories. So these are considered to be benefits of fiber consumption by FDA. All right, cellulose. So one of the classic insoluble fibers, at least as is called cellulose. So if we look at cellulose, it is a beta-1,4 bonded glucose polymer. So that beta, as we've tried to emphasize in class, signifies that it's going to be difficult to digest. One of the other outcomes of having a beta-1,4 bonding rather than an alpha-1,4 bonding is, rather than having phone cords, this sort of spiral type of a characteristic to it, we make flat sheets, or cellulose makes flat sheets. And so it's different in terms of its structure. Once you bond a bunch of these beta-1,4s to one another, they tend to make these flat sheets. They tend to be more rigid, and they're not as easily associated with water. But they do hydrogen bond to one another, these long chains of beta-1,4 glucose, and so they make important structures, including, as far as we're concerned, things like paper and cardboard. So cellulose, it's found naturally in cell walls. It is part of the protective outer layer of cell walls, and it forms fibers. And so you have fibers which are made up of smaller and smaller components, microfibrils, and then actual glucose polymers themselves, all beta bonded. And so this is part of the tough outer layer of cell walls. You can change some of the structures of cellulose and turn it into something called microcrystalline. And so the idea is that, much like a starch granule, cellulose has both amorphous or glassy regions and crystalline regions, just arranged somewhat differently because cellulose is a bit more fibrous. If you use a mild acid treatment, you can break up some of those glassy or amorphous regions, and you might remember back to the depolymerized starch that we talked about a while back. What this does is it will help increase viscosity, and you can use this microcrystalline cellulose as a bulking agent. We see this now over and over again. Sugars as bulking agents, starches as bulking agents, things that can be used to dilute other materials if we wish. So CMC, or carboxymethylcellulose, has added carboxylic acids, and so in addition to the glucose functionality, the fact that it has carboxylic acids, and those have a pKa of 4.3, means that depending on pH, it's going to be negatively or positively charged or potentially neutral. All of those can affect its ability to associate with water. So now we can go from cellulose, essentially insoluble in water, to something that is highly soluble and works very well as a thickener. And it's based on the functionality of these carboxylic acid side groups. All right, so methylcellulose is another type of this molecule, and you can see here that we've replaced a few of the hydroxyl groups with methoxy groups. The idea then being that these methoxy groups encourage hydrophobic interactions, and hydrophobic interactions tend to be encouraged at higher temperatures. This is why this type of cellulose in particular will tend to gel as temperatures rise. So it's a bit strange. It will gel as temperatures rise. When it cools, the gel melts. This is exactly the opposite of almost all other polysaccharide type gelling agents, which typically rely on either hydrogen bonding or some type of ionic bonding, or maybe both. So this is a bit strange in terms of the way it performs, but very helpful if you want something to thicken when it's being cooked or when it's hot, and then to thin back out when it's cooled back down. So it's quite useful for that purpose. And there you can see just a bit of a magnification of those methoxy groups. All right. So not only can we get cellulose type materials from plants, but we can also get cellulose, or modified cellulose in this case, from microbes. So xanthan gum, you may have heard of this, especially if you're into making gluten-free foods or buying gluten-free foods. Often you'll see xanthan gum as part of this, and this was produced as one of the first biotechnology-related ingredients. So we grow up a bunch of microbes and we harvest this material that they produce. It will hydrate in cold water. These side chains help it to do that, and it produces very high viscosity. It's used in a lot of different types of foods, primarily for this thickening type of effect. Beta-glucan is by far, at least the beta-glucan found in oats and barley, is by far my favorite soluble fiber. And I want to point out what makes this beta-glucan different, because if you look at the literature, you'll see that beta-glucans are produced by yeast. They're produced by other types of microbes, and technically you could make the argument that cellulose is a kind of beta-glucan, but this beta-glucan in oats and barley is soluble, unlike typical cellulose, because it has both beta-1,3 and beta-1,4 glycosidic bonds. So the beta means that it's not digestible by our human apparatus, but the fact that it has both beta-1,3 and beta-1,4 allows for a bit more molecular flexibility, not as rigid of a molecule, and that helps to make it more soluble. So this will be a soluble type of a fiber. All right, so the take-homes for this fiber lesson would be that fiber has variable structures. It's mainly found in plants, a few exceptions. You can see that microbes can do that too, but it's about beta bonding, bonds that we cannot break, and the idea that we're dealing in terms of cellulose with glucose polymers, and glucose polymers with different types of modifications. So those are the take-homes for this fiber lesson. Hope you've enjoyed it, and we will see you for the next one. Bye.